Swayam Prabha. Digital India. Educated India.
Welcome to Flow of Water Through Soils, lecture number 3. In the previous lecture, we have introduced what will happen to the effective stress when water flows through soils, and we discussed 3 cases. One is no flow condition, another case is when the flow is taking place in the downward direction, and finally we discussed about an upward flow condition. Then we said that depending upon the direction of the flow, whether it is upward or downward, there will be a change in effective stress. In case of downward flow, we have said that there will be an increase in effective stress. In case of upward flow, we said that there will be a decrease in effective stress. In case if the head loss which can reach to a critical head, then we said that that particular head can be called as critical hydraulic gradient, at which effective stress is equal to 0, and that condition we have defined as quick condition or boiling condition. Thereafter, we have discussed about the practical problems or places where the quick conditions can occur, and we also discussed about quicksand is not a type of sand, but a flow condition where water flows in the upward direction. So, the submerged weight of the sand is balanced by the upward thrust exerted by the water, and that condition simulates a case where sigma dash is equal to 0. So, in this present lecture, we will try to understand much about the seepage pressures, and then we will try to deduce an expression for seepage pressure, and thereafter we will try to solve some problems in the effective stresses, particularly when the flow is taking place in upward direction, and a problem in which the excavation, how excavations in the soil when it is having a layer under artesian conditions can create problems. So, this is our the previous talk where we discussed about the fluid flow through soils and flow of water through porous media. Then we said that the changes in geostatic stresses with the flow of water through soils that we discuss, and quicksand condition or boiling condition that we defined and tried to discuss. So, in the when you consider the case 3, that is upward flow condition, when flow takes place through soil in the upward direction, that means that if there is a H which if H is the head loss, then what will happen is that drives the flow in the upward direction. So, in the process what will happen is that when the flow is taking place from this point to this point, because to enable the flow to take place, it loses the energy which is driving that. So, the energy which is available here will be lost here. So, in the process what will happen is that there will be a decrease in the pore water pressure. In the process, when you take the difference of total stress and pore water pressure, then we said that yields as something called there will be an increase in the pore water pressure. Because of that, because of this, then there will be a decrease in the pore water pressure. You can see the decrease, the increase is compared to the one with the no flow condition. So, consider now like seepage forces. These are the forces which are responsible because when the flow is taking place through the soil, that is exerted by onto the grains in the form of a frictional drag as well as viscous drag because of the permeant under consideration. So, when water flowing past a soil particle exerts a drag force on the particle in the direction of the flow. So, you consider in this slide which is shown here a container having frictionless boundaries, having a surface area perpendicular to the plane of this figure. The surface area is around A, length of the sample is around L. Then it is under saturation, assuming that a sand which is there under saturation with certain density, and a water level is maintained here. It is connected to a stem and placed at a height h above this level. So, the hydraulic gradient in this case is h by L, that is the hydraulic gradient, and so the flow takes place in this direction, in the upward direction. So, when in the direction of the flow, if you consider a single grain, if you pick a grain from here and then consider its equilibrium, then what will happen is that this WD is the weight of the dry solid grain, and FSC, they are the seepage forces acting on both sides of the grains, which are because of the frictional drag as well as the viscous drag of the viscous drag imposed on the particle, and B is the buoyant weight. So, if you consider the equilibrium, then we will be able to achieve an expression for the seepage force. So, the drag force is caused by the pressure gradient and viscous drag, that is what we are discussing. The drag force which is here shown caused by the pressure gradient in the form of a frictional drag and by viscous drag. So, water flowing past a soil particle exerts a drag force on the particle in the direction of flow. So, it depends, for example, if it is happening in the direction of the flow, if it is downward direction, then what will happen is that there will be increase in the packing of these particles because they are tucked into the closer positions. So, there will be an increase in the effective stress. In the case of upward flow, what will happen is that the particles will be disturbed, and in a way there will be a reduction in the effective stress. So, if the head is increased continuously, then what will happen is that a particular head, when it reaches h is equal to hc, then a critical condition can exist. So, that we call as quick condition. So, in connection with this, we will try to solve some problems also. With that, we will be able to clear about this concept. So, considering this free body diagram of soil mass as well as the solid grain, let us try to derive about an expression for seepage force. So, considering now this is the direction of the flow which is in the upward direction, and seepage force acting in this direction. So, this is the base of the sample where the water pressure is acting because of the head which is causing the flow, and W is the weight saturated unit weight of the soil mass, entire soil mass. So, now if you consider this at critical condition, that means that at critical condition when H is increased gradually such a way that H attains Hc. So, Hc here is defined as a critical head. So, when this happens, Gs plus E by 1 plus E gamma W AL. So, Gs plus E by 1 plus E gamma W AL. So, this indicates something like there is the saturated unit weight of a soil mass. There is an expression for a, we know that for a two phase system under saturated conditions, gamma sat can be written as Gs plus E gamma W by 1 plus E. A is the area of the cross section over which the flow is taking place, L is the length of the sample. So, this is the weight, saturated weight of the soil mass, that is W, which is at the base, which is resisted by Hc plus L, that is Hc is the head which is causing the flow, L is the length. That means that the head which is there, the pressure head, the pore water pressure head which is there at the base of the sample is Hc plus L. So, that is nothing but the U is nothing but Hc plus L into gamma W, where gamma W is the unit weight of water. When you equate this, then we get I is equal to Hc by L is equal to Gs minus 1 by 1 plus E. So, this indicates that Hc by L is the critical hydraulic gradient at which the Gs minus 1 by 1 plus E. So, when we have discussed that this critical hydraulic gradient is mostly equal to 1 for most of the soils, and for specific gravity typically for sands GS is equal to say 2.65, then IC will be equal to 1. So, it depends upon the packing density at which these particles are there. So, in loose sands and silty sands, this particular condition is ought to occur. Particularly for clay soils, this will not occur because there will be a permanent cohesion which keeps the particles binded together. So, in the process what will happen is that it cannot overcome this quick condition cannot be created to a great extent. Whereas, in case of boulders where they have got very high sulfate, because of that again they will not be able to get lifted up to, or they will not be able to be segregated such a way that they cannot be agitated in other means, so that this quick condition cannot occur. So, by considering this now considering this free body diagram of a grain alone, let us try to derive the an expression for seepage force. So, considering the free body diagram of the grain in the direction of the flow at I is equal to IC. So, we will derive for I is equal to IC an expression for seepage force, then thereafter we will try to deduce a general expression for a condition which is other than critical hydraulic gradient condition. So, as we have seen, the weight of the particle, that is dry particle, is acting downwards and the frictional drag is acting in the direction of the flow, and the buoyant weight is opposing the sulfate of the particle. So, by taking vertical equilibrium, we can write WT is equal to WD is equal to Fs suffix C plus B. By rewriting this, Fsc is equal to WD minus B. Now, by writing the expression for from the two phase system, Gs gamma W by 1 plus E, that is nothing but the gamma D, that is the dry unit weight of the dry density or dry unit weight of the soil into AL. A is the area over which the flow is taking place, L is the length of the specimen. So, this leads to Gs gamma W by 1 plus E into AL minus buoyant force is nothing but the volume of the solid grain into gamma W. So, Vs gamma W is the buoyant force. Now, simplifying this further, Gs gamma W by 1 plus E into AL minus, now this Vs can be written as V minus volume of voids, that is total volume minus volume of voids divided by volume of voids into divided by volume, total volume into volume. So, the Vs is written here as V minus Vv by V into V. So, that can be simplified as 1 minus n, where n is the porosity, into AL. AL is nothing but the, because of the volume is equal to AL into gamma W. So, the frictional force or drag force acting in the direction of the flow is nothing but Gs gamma W by 1 plus E into AL minus 1 minus n into AL gamma W. So, this if you further simplify this, we will be able to get Fsc is equal to Gs minus 1 by 1 plus E gamma WV, because n is equal to E by 1 plus E. By substituting that, we will be able to get frictional drag force Fsc in the direction of the flow is equal to Gs minus 1 by 1 plus E into gamma WV. So, here this Gs minus 1 by 1 plus E can be written as from the previous deliberation can be written as IC, that is the critical hydraulic gradient. So, seepage force is equal to IC gamma WV. So, this is also called or indicated by seepage force Js, J suffix S, and also termed as weight of the fluid phase undergoing this particular flow phenomenon. So, the seepage pressure is again nothing but seepage force per unit volume. So, in that case P suffix S seepage pressure is equal to IC gamma W. So, for the cases when head is less than Hc, when the head is less than Hc, when the head is less than critical hydraulic gradient, then Fs continues to be in terms of like Js is equal to I gamma W V, where V is the volume of the soil where the flow is taking place, and gamma W is the unit weight of water, then I is the hydraulic gradient. So, for if H is less than Hc, then Cps force Js is gamma I gamma W V. So, what we try to derive is that an expression for Cps force and Cps pressure, and the units for Cps pressure are same as that of the unit weight units like kilonewton per meter cube in SI units. So, the critical hydraulic gradient and the quick condition. The quick condition occurs at a critical upward hydraulic gradient when Cps force just balances the buoyant weight of an element of the soil. That is what we have previous slides, we tried to use this concept and derive an expression for critical hydraulic gradient and Cps force. Shear stresses on the sides of the element are neglected. So, the assumption is that the shear stresses on the sides of the element are neglected. So, we can write in terms of IC can also be like Gs minus 1 by 1 plus E. When 1 plus E is termed as a specific volume, then we can write like IC is equal to Gs minus 1 by specific volume. So, the critical hydraulic gradient is typically around 1 for many soils. We have, that is what we have discussed, the critical hydraulic gradient is equal to 1 for most of the soils. This condition, apart from creating problem in for the or affecting the stability of the geotechnical structures, they are used also effectively in particular other disciplines like chemical engineering. Like fluidized beds in chemical engineering system rely on the deliberate generation of quick conditions to ensure that the chemical process can occur most efficiently. So, fluidized beds in the chemical engineering systems rely on the deliberate generation of quick conditions to ensure that the chemical process can occur most efficiently. So, the fluidized beds while designing, they are designed such a way that this quicksand condition occurs and creates this agitation of the particles, so that the chemical process can occur more efficiently. So, it has got merit in terms like can create or accelerate or get the efficiently the chemical process to take place for fluidized beds. So, let us look into, having seen the theory, now let us look into some problems, particularly the example problem which is shown here is the similar arrangement, but here assuming that there is a saturated sand with a unit weight gamma sat is equal to 20 kilonewton per meter cube, and which has got a water which is resting above the top surface of the sand, and this is the level which is maintained here, and the stem is connected, and which is at a height h above that there is a water level maintained. So, what we are the problem example problem runs like this: determine and plot total stress, pore water pressure and effective stress diagrams at A, B, C, D. If h is equal to 1 meter in one case, that is case 1, we call it is case 1, case 2 h is equal to 4 meter, case 3 h is equal to 2 meters. So, if you look into it, the generalized expression I is equal to h by 2, because L length over which the flow is taking place is 2 meters. So, I is equal to h by 2. For the case 1, now the hydraulic gradient I is equal to 0.5, that is because h is equal to 1 meter, 1 by 2 0.5. In the case 2, in the case of case 2, I is equal to 4 by 2, that is 2. In this case, I is equal to 1. Let us see with this different hydraulic gradient conditions how this problem can affect the solution. So, in this problem, at this particular level is considered as datum. So, at D level, the plane passing through point D is considered as a datum uniformly throughout for all the cases. So, C is a point which is at the midpoint of B and D vertically. Now, let us look for the case 1, I is equal to 0.5. If you look into this, at point A, which is elevation is 4 meters, that means that point A is 4 meters above this point. So, the elevation head is 4 meters, and the pressure that is the pressure head which is raised about this point is 0. So, the total head at this point is pressure head plus elevation head, pressure head is 0. So, total head is equal to 4 meters. Here what will happen is that the elevation head is 2 meters, the pressure head is 2 meters. So, total head is equal to pressure head plus elevation head is equal to 4 meters. Now, when you come to this point, now this point if you take h is equal to 1 meter, which is 2 plus 2 plus 1 5. So, it has got a pressure head of 5 meters. Elevation head is 0 because it is at the datum. So, the total head will have to be 5 meters. So, if the head loss is say 1 meter, so here the total head has to be 4 meters. So, that the total head loss which is occurring, that means that here we will have a triangle which is 1 meter and which is 0. So, the hydraulic gradient is with an hydraulic gradient of 0.5 the flow takes place. So, that is what has been discussed here. B, which is having pressure head of 2 meters, elevation head of 2 meters. So, total head will be 4 meters. In case of D, we will come to C later, where pressure head we said as 5 meters, because this D is at the datum. So, elevation head is 0. So, total head is 5 meters. C, the total head will have to be 4.5 meters, because already at midpoint the 50% of the head loss would have already occurred. That means that the head loss which is taking place between points D and A, D and C, or D and B, they are it is around 1 meter. That means that at midpoint around 50% of the energy will be lost. So, the total head will be somewhere around at D it is around 5 meters, at C at the midpoint when the 0.5 meter head loss has already occurred. That means then what will happen is that the total head is 4.5 meters. Now, elevation head is 1 meter because the C is 1 meter above the datum. So, the pressure head has to be 3.5 meters. That means that much pore water pressure has got dissipated. So, in the problem here, the problem here 3.5 meters, the total head is 4.5 meters, elevation head is 1 meter. So, the pressure head here is 3.5 meters. So, let us try to construct total stress, pore water pressure and effective stress diagrams. If you look into this, for case 1, I is equal to 0.5, that is H is equal to 1 meter. Then if this is the datum, D and B, the flow is taking place in the upward direction and with an hydraulic gradient of 0.5. Then A is the topmost point, D is the point at the datum and B is the top surface of the soil. B is at the top surface of the soil. Then the total stress here at this point is 0, at this point is 20 kilonewton per meter cube, 20 kilonewton per meter square. At this point it is 40 kilonewton per meter square, because 20 plus that is 10 into 2, 40 kilonewton per meter square, and then here it will be 60 kilonewton per meter square. When you come to the pore water pressure, so we have discussed here the head which is there is 5 meters. So, the pore water pressure is 50 kilonewton per meter square, where U is equal to where gamma W is equal to 10 kilonewton per meter cube is considered here. So, 335, that is because 3.5 meter is the pressure head which is available, because 0.5 meter head loss has already occurred from when the flow is taking place from D to C. So, in the process what will happen is that here at this particular point it is the pore water pressure is 35 kilonewton per meter square, and at this particular point it is 20. So, when you determine effective stress, that is difference of total stress and pore water pressure. So, effective stress is equal to at this point it is 0, at this point it is 0, and here it will be 40 minus 35 5, and here 60 minus 50 10. That means that at this particular point a effective stress which is maintained here is still positive. So, for this condition of case 1, so we have determined based on total heads and elevation heads and pressure heads, we try to determine the effective stress at effective stresses at different points, and then we try to use D as the datum in this particular case. Now, let us consider a case 2 where I is equal to 2 meters. That means that I is equal to 2 that is H is equal to around 4. So, when you maintain H is equal to 4, so I is equal to 4 by 2, where 2 is the length of the flow in this present case 2. So, if you look into this, A which remains same, at the pressure head is 0, elevation head is 4 meters. So, total head is 4 meters, and B which is pressure head is 2 meters, elevation head is 2 meters. So, total head is equal to pressure head plus elevation head is equal to 4 meters. But when you come to D, now there is a head of 4 meters is there, plus 4 plus 2 plus 2, so around 8 meters pressure head. So, elevation head is 0 because it is at the datum. So, the total head is equal to 8 meters. So, if you compare D to B, there is a 4 meter head loss has occurred. So, 4 meter head loss is occurring over 2 meters, that means that the hydraulic gradient is equal to 2. So, at D, the head which is available for driving the flow is around 4 meters, at B it is 0. That means that when the flow is taking place, then what will happen is that energy is lost in the form of frictional drag transferred to the solid particles. Now, let us see what will be the head at C, which is the midpoint of D and B in the direction of the flow. So, now that at D, like in the previous case, now we have got a head of around 8 meters. That means that at B it is now the head of around 4 meters. So, at C 50% of the head loss will occur, that means the 2 meters will be already lost. So, in the process what will happen is that the total head which is available now is 6 meters at C, because already 2 meters has been lost. Elevation head is 1 meters. So, the pore water pressure head will be around 5 meters. So, the pore water pressure available now here is around 50 kilonewton per meter square, if you consider gamma W is equal to 10 kilonewton per meter cube. Now, let us look the similar case 2, H is equal to 4 meters, the total stress remains same, and pore water pressure now we change accordingly here 20, that is at this particular point. Now, at this particular point it is 50 because that the head loss is occurred, and 80 here because the head which is driving now is 4 plus 2 plus 2 is around 80 kilonewton per meter square. Now, the difference of total stress and effective stress, that sigma dash, so is now 0 here and 0 at this particular point, and here total stress minus pore water pressure, now it is something called an effective stress is negative. So, here 60 minus 80 is around minus 20. So, these negative effective stresses, they do exist, particularly in the condition where the quicksand condition would already occurred. So, this is a condition where the quick condition would have already occurred, because the negative stresses indicates that the particles are in agitated motion and no interaction. So, such a way that the pressure is very high, the pore water pressure is very high, and they are not able to generate any intergranular stresses. So, this negative effective stresses, they do exist, particularly a case in agitated or boiling condition. So, in this particular case too demonstrates that a condition where quick condition would have already occurred. Let us now consider case 3. Having seen case 1 and case 2, let us see case 3, where the hydraulic gradient is equal to 1. That means that I is equal to 1. So, for that length of the flow is 2 meters. So, head loss is around 2 meters. So, in the case 2 by 2, which is equal to I is equal to 1. So, if you look into the same deliberation again at different locations A, B, D and C, the pressure heads will be same here at A and B, but the only difference here is at D, now it is 2 meters which is above the upstream level, above the point A. That means that now the total head available here is 6 meters. So, elevation head is 0. So, the pressure head is around 6 meters. At C, because the head driving the head loss which is 2 meters. So, at C 50% of the loss would have already occurred. That indicates that the pressure head will be around 4 meters, total head will be around 5 meters. So, elevation head is 1 meters. So, the pressure head will be around 4 meters. So, now if you look into this condition like H is equal to 2 meters, case 3 where the hydraulic gradient equal to 1. So, here total stress remains same, and pore water pressure now at this particular point it is 2 plus 2 plus 2 6, and here that is 6 into 10 60 kilonewton per meter square, and here it is 40 and here it is 20. So, in the process now, if you take the difference of total stress and effective stress at all points here, you will see that effective stress is 0. That means that this particular condition just attained quick condition. So, just attained quick condition is the case where sigma dash is equal to 0. So, here now this head which is h is equal to 2 meters can be said as critical head which is causing a flow to take place in the upward direction and imposing an effective stress equal to 0. So, having seen a particular case and how to determine and ascertain the pressure heads, and by using the principle what we discussed from the total head is equal to pressure head plus elevation head, and then we try to discuss about a case where the hydraulic gradient gradually changes to a critical hydraulic gradient, a case where even negative effective stresses can occur even for case where the quick condition would have already occurred. So, let us now consider from this example problem where the boiling condition generally occurs in geotechnical structures when excavations takes place in a particular soil. So, in this case a stiff clay is underlined by a sandy soil. Suppose this sandy soil, due to some reasons, if it is subjected to additional head of water, due to this condition is also called as artesian condition, where if it is able to, if it has got a source of water which is trapped inside, can impose upward forces onto the soil. So, as long as this excavation is not there, so this pressure is not adequate to induce a failure. But when we excavate for installing some utilities, underground utilities or so, then these failures there ought to take place in 2 to 3 hours time. So, here this problem says that the sand layer of the soil profile is shown in the figure under artesian pressure. That means that here the pressure which is artesian pressure has been determined is around 5 meters. That means that if investigation has been done carefully, then this type of failures can be prevented by adopting suitable remedial measures. So, let us consider a case where we know that there is an artesian head of 5 meters which is occurring here. So, the entire sand which is here is saturated and which is under artesian head conditions. A trench is to be excavated in the clay up to a depth of 4 meters. So, the depth of the 4 meters is defined here, which is in the stiff clay having a unit weight gamma is equal to 18 kilonewton per meter cube. So, determine the depth of the water H to avoid boiling. So, in case the boiling phenomena occurs, then what is the height of the water I should maintain to prevent any boiling failure. So, let us see the solution. Here now this excavation takes place, so this much soil will be removed. So, at P, so at this particular point interface of the stiff clay and sandy soil, so consider a point P where total stress is equal to gamma W H. So, this H is unknown to us. Let us term this the height of the water which is required to be determined in this problem as H. So, gamma W H plus 6, the 6 meters is the thickness of the soil layer above the sand layer. So, 6 minus 4, that is 4 meters is the depth of the excavation. So, 6 minus 4, that means that much clay has already been removed. So, now the existing one is 4 meters already has been removed. So, 2 meters is still remaining there. So, at total stress is now there is a decrease in total stress because of the excavation. So, gamma WH which is required to be determined plus 2 into gamma clay. Now, at P, for example, if this is the area over which this upward thrust is exerted at the point P or a plane area A, then U is equal to 5 gamma W. That is nothing but 5 meters is the head which is causing the flow and gamma W is the unit weight of water. So, at P, effective stress is equal to total stress minus pore water pressure. So, by equating now gamma WH plus 2 gamma clay minus 5 gamma W. So, for boiling condition, like in the previous case, we can impose a condition like sigma dash is equal to 0. So, by imposing this condition here, we can determine that h is equal to 1.33 meters. So, this indicates that to prevent the boiling condition, we have to maintain minimum around 1.3 meters of the height of the water in the trench. Otherwise, there is a eventuality of occurrence of boiling condition. In the similar lines, let us look this example problem. A large open excavation was made in a stratum of clay with a saturated unit weight of 17.6 kilonewton per meter cube. When the depth of the excavation reached 7.5 meter, the bottom rose in the sense heaved up, gradually cracked and was flooded from by a mixture of sand and water. So, subsequent investigations showed that the clay was underlain by a bed of sand with its surface at a depth of 11 meters. So, the clay thickness was around 11 meters. Compute the elevation for which the water would have risen from the sand surface into a drill hole before the excavation was started. So, the solution works out like this. We have got a thick clay layer which is around 11 meters, having a saturated unit weight equal to gamma sat is equal to 17.6 kilonewton per meter cube. So, the excavation which has been taking place here is that 7.5 meters. So, after reaching a 7.5 meters depth, then it was observed that the bottom of the excavation heaved up and undergone a failure, which has reflected in the form of a collection of sand and water. So, subsequent investigations have shown that the thickness of the clay layer in which the excavation is being carried out is around 11 meters. That means that at the end of the 11 meters, the sand surface is starting. So, if this particular sand layer this would have caused this type of heaved failure, means it would have been under artesian conditions. So, the investigations or calculations can be carried out. What would have been the height of the water which would have risen in the standpipe before excavation, if suppose if it would have been measured. So, if the excavation is carried out at 7.5 meters, now we need to calculate that elevation h to which the water would have risen into the standpipe. So, here again consider point A, which is interface between clay layer and sand layer. So, at this point, this particular portion say area A perpendicular to the plane of this figure is subjected to an upward thrust, which is say gamma W h. So, in this case gamma W is equal to consider here as 10. So, it is 10 h kilonewton per meter square acting over area A in the upward direction. Now, here at this particular point, here the net total stress which is remaining is nothing but 11 meters minus 7.5. So, around 3.5 meters of soil which is resting at that particular time when the excavation is reached around 7.5 meters. So, for the boiling condition or quick condition, we say sigma dash is equal to 0. So, for that equating total stress is equal to total stress is equal to the pore water pressure at this particular base of the soil layer, that is interface here. So, 17.6 into 11 minus 7.5 into 10 into h, by equating that we get h is around 6.16 meters. So, the elevation for which the water would have risen from the sand surface into a drill hole before the excavation was started, will be around h is equal to 6.16 meters. So, having this seen, now let us try to consider another problem which is again under artesian conditions, but here we are required to determine the effective stress distribution profile at point A and C and B, where C is at a point 1 meter above the this datum, B is the datum level. So, the soil strata which is shown here, D is the datum which is the plane which is undergoing the called as datum in this problem is B, passing through B, and C is 1 meter above datum, A is 3 meters above datum. So, thickness of the clay layer is around 3 meters and the gamma clay is around 17 kilonewton per meter cube. The groundwater table is resting here is located here, which is 2 meters above point A. Then above that 1 meter there is a sand which is dry, gamma d is equal to 18.5 kilonewton per meter cube, and now it is having because of the artesian conditions, it is having a water head 1 meter, total head is around here, it is around 1 meter above this ground surface. So, this is the existing ground surface. So, if you look into this now, the head loss, which is nothing but difference of water levels between this level and this level, is around 2 meters occurring over the layer which is undergoing. So, if you consider only the flow which is taking place in the clay soil, ignoring this sand here, then from B to A, if you consider this flow which is taking place from B to A in the upward direction, because the flow occurs in upward direction because of the head which is driving the flow from this level point B to A. So, here now the hydraulic gradient is somewhere around which is nothing but 2 is the H and L is around 3 meters. So, hydraulic gradient is around 2 by 3. So, if you consider at this particular point the total head which is available is around 2 meters, then afterwards here that head energy, which is the total complete loss of energy, occurs by the time it reaches point A. So, at this particular point, if you look into it, then there will be a certain loss of the energy takes place, then and further loss of energy takes place once the water passes point C and which is traveling towards point A. So, here total head at A, if this is started as a datum, so we can say total head at A is equal to elevation head is total head at A will be, it will be, if I tap the if we put a standpipe here, it will rise to 2 meters, because already when the water traveled from B to A, then the whole complete head loss is already occurred. So, at this particular point only it will rise to 2 meters, that is because of the standing groundwater table. So, here this elevation head is now 3 meters. So, if you consider now pressure head is 2 meters, elevation head is 3 meters, the total head at this point is A is 5 meters. At point B, now if you look into here, it is at the datum. So, elevation head is equal to 0 and total head is 3 plus 2 that is 5 plus 2 that is 7 meters. So, here it is subjected to around 70 kilonewton per meter square, that is pressure head is around 7 meters, because elevation head is 0, the total head is also equal to 7 meters. So, the difference of total head HB is around 7 meters, HA is around 5 meters. So, HB minus HA, that is 2 meters, that is the delta H occurring over a length equal to which is 3 meters, that is 2 by 3, that is the hydraulic gradient in this problem. So, here at point C, if you look into it here, here is the head which is available, total head which is energy delta H which is available is HB minus HA is around 2 meters. At this particular point already 0.67 meters of the head is already lost. That means that now 1.33 meters head is available to be spent in the while enabling the flow to take place through the soil. So, by the time it reaches this point A, that delta H is equal to, that head loss will be equal to 0. So, here at this particular point C, it is around 1.33. So, further we look this problem in determining effective stresses at A and C and B. So, from the discussion what we had so far, at point B total stress is equal to 18.5 into 1 plus 19 into 2 plus 17 into 3, which yields to around 107.5 kg per meter square. The pore water pressure is around 10 into 7, that is 70 kg per meter square. So, effective stress is nothing but the total stress minus pore water pressure. So, that is equal to around 37.5 kg per meter square. That means that we have tried to determine this total stress at this particular point B and pore water pressure at this point B and effective stress at this particular point B. Similarly, at point A, then we get sigma u and sigma dash. So, they run out like this. Now, let us consider at point C. At point C, which is 1 meter above the datum. Sigma is equal to 18.5 into 1 plus 19 into 2 plus 17 into 2, which is around 90.5. Now, we have the this 10, which is gamma W, which is considered unit weight of the soil water around 10 kg per meter cube, into the pressure head at point C is 5.33. How we are going to see? So, it is around 53.3 kg per meter square, and the sigma dash, which is total stress minus pore water pressure, yields to be around 38.2 kg per meter square. So, the total head at C is determined like this: total head at B minus I Z. So, if that is Z from the in the direction of the flow at Z is equal to 0, that means that the full head is available. So, it is 7 meters is the head which is available there. So, here if you put here as the at this particular point I is 2.2 by 3 and Z is equal to around 1 meter. So, the total head at C should be around 6.33. That means that 0.67 meters of the head is already lost. So, that is what actually we are discussing while introducing this problem. So, now the pressure head available at point C is equal to total head at C minus elevation head at C. So, elevation head at C is 1 meters. So, by subtracting 1 from 6.33, we get 5.33. So, that is how we determine the pore water pressure at C when the flow is taking place from B to A, and C is 1 meter above the datum. So, now let us try to plot whatever we have determined for this case. B is the datum and C is a point where 0.67 meters energy is already lost, that is head loss is already occurred, and at this point complete head loss is already occurred. Here the full head of 2 meters which is driving the flow is available. Now, in this case the total stress, which is 56.5, 90.5 and 107.5, this will be because of the self weight, that is geostatic stresses, and here these are the pore water pressure, this is which is 20 at this particular point, because 20, because here if I put a standpipe it will rise to 2 meters here because of the virtue of the groundwater table here existing at this particular point 2 meters above point A. So, here at this particular point here, because there is a energy which has been lost from B to C. So, because of that what will happen is that the pore water pressure is now 90, the total stress is 90.5, the pore water pressure is 53.3, the difference of total stress and pore water pressure yield an effective stress which is around 38.2. So, this is the effective stress distribution sigma dash, and this is the pore water pressure distribution, and this is the total stress distribution. So, in the given problem, given strata has been given, and we have tried to based on the concept what we try to understood, we have tried to determine the distribution of the total stress and pore water pressure and effective stress when the flow is taking place in upward direction because of the some artesian conditions of the underlying clay layer, underlying sand layer below the clay layer. So, here because of this particular clay, the flow by knowing its relevant properties, even we will be able to estimate seepage pressure or seepage forces within the clay soil also. So, like seepage velocity can be estimated by calculating from the when you know the coefficient of permeability value. So, this coefficient of permeability value, which is also called as Darcy's coefficient of permeability, is an important parameter which is can be determined either in the laboratory or in the field tests. In the laboratory we have also direct and indirect methods. Like indirect methods involve from the grain size distribution one can determine, or as well as from the indirectly from the consolidation test data we can also determine the permeability. So, the measurement of the soil permeabilities, where the rate of flow of water Q, that is volume per time through a cross sectional area A, is found to be proportional to hydraulic gradient I according to Darcy's law. This is what we have discussed. So, V is equal to Q by A, where A is the area over which the flow is taking place, the perpendicular to the direction of the flow. A is the cross section area perpendicular to the direction of the flow, and K is the coefficient of permeability or Darcy's permeability, and I. So, this is according to Darcy's law, the rate of flow of water Q, that is volume per time, through cross section area A is found to be proportional to hydraulic gradient I according to Darcy's law. I is equal to H by L. So, where V is the flow velocity, which is also called as the discharge velocity or superficial velocity occurring over an area A. So, the coefficient of permeability of soil is a measure of the conductance, which is nothing but the reciprocal of the resistance in electrical terms, that provides the that it provides to the flow of water through its pores. So, the conductance, that is, it provides to the flow of water through its pores. So, the coefficient of permeability of soil is a measure of the conductance that it provides to the flow of water through its pores. So, as we have now different types of soils like sandy soils and clay soils, then they are different in the soil structure, they differ in its type of a soil and composition. So, all these factors will affect in permeability in having a difference in the permeability values. So, the measurement of the permeabilities, for example, if you look into it, the volume of coefficient of permeability K depends upon average size of the pores. The pore space is very important here. The smaller the pore space, then the slower is the flow which can take place. So, average size of the pores is related to the particle sizes and their packing. So, the value of the coefficient of permeability K depends upon the average size of the pores and is related to the particle sizes and their packing. So, we have discussed it during the capillarity condition or capillarity phenomena. We said that D, which is nothing but the pore space, is approximated as ED10, where E is the void ratio and D10 is the effective particle size. So, if the effective particle size of a clay soil when very small, then we can expect very minute miniature pore spaces for clay soils. So, it has got a different value for permeability for clay soil. The particle shape depends upon the particularly for gravel soils, gravelly soils or sandy soils. This particle shape has got a influence in the permeability, that is in the form of a shape factor which is taken. We will be discussing in detail in the next class. In the soil structure or the soil fabric and arrangement, like which arrangement for sandy soils, either the loose or dense, that is the packing which will affect, or in case of a clay soils, whether it is a flocculent or disperse, so that can influence the permeability value. So, the ratio of the permeabilities of the typical sands, gravels to those of typical clays is of the order of 10 to the power of 6. As we already discussed and mentioned, if you look into this, the ratio of the permeabilities of a typical sands, gravels to those of typical clays is of the order of 10 to the power of 6. A small proportion of the fine material in a coarse grained soil can lead to a significant reduction in the permeability. A small proportion of the fine material, that means that if you have got in a gravelly soil a clay which is making the gravelly soil to behave like a gravelly clay or so, then it can change its permeability characteristics and can impose impervious characteristics to the particular soil. So, a small proportion of the fine grained material in a coarse grained soil can lead to significant reduction in the permeability. So, that is the reason why it is very important to know about this permeability value and its effects, because ill effects induced in affecting the performance of the geotechnical structures like parking lots which are designed for drainage, where this particular facility will not achieve, market yards or different types of structures which do affect and require to be designed with due consideration. So, in the next class we discuss about how to measure this permeability. There are two methods are there, like laboratory methods we do for a highly permeable soils, we use constant head permeameters, and that is called constant head test, and for relatively impermeable soils like clay soils or fine grained soils, we use falling head test or variable head test. And indirect methods, as we discussed, like computation from the grain stress distribution or from the iodometer while performing a consolidation test. So, in the field also this permeability is required to be estimated, like from the pumping methods or borehole methods. So, these tests will try to yield permeability value. Particularly the Packus tests are very famous in determining the field permeability values in Ligons in the field, that we will discuss in the future in the forthcoming class. So here in this, what we introduced is that the measurement of the soil permeabilities like laboratory methods and field methods. So we start with the laboratory methods, and then we also discuss the methods which are available in the field, and then we will be introducing the factors affecting the coefficient of permeability, particularly like what are the different types of soils and how and why a sandy soil and a clayey soil is said to have a different permeabilities, how far this mineralogy and the soil structure coming into the picture in affecting the permeability.